So recording is on. It's March 26, 2021. And oh yes, Sam, we were just talking about this. Vaccination is open to all adults. Yes, starting March 30th in Minnesota. Woohoo. Hallelujah. All right. So in other great news, we've been making progress. We are getting somewhere in terms of understanding how these piecewise polynomials might be the same as the Stanley-Reasoner ring for a simplicial complex when we have a simplicial fan. Not necessarily complete, but just all cones being simplicial. And what we were doing last time was kind of the key step, really. What we proved was this proposition that says, and this is from one of those Brion papers that's on the syllabus, 96 one. If you've got a simplicial fan, capital sigma in RD, and you pick a maximal cone, little sigma, then you can think about it inductively. The ring of piecewise polynomials on the whole fan, you can restrict those to the fan in which you just poke out the cone sigma. You take out that maximal cone, and what's left will be a sub-fan. And there's always a restriction map from piecewise polynomials on a fan to piecewise polynomials on a subfan. And it turns out to be surjective, and we can identify the kernel. The kernel is just all multiples of this one piecewise polynomial that we call G sub sigma for the cone sigma. And what we proved last time is that not only is this the kernel, so we get a short exact sequence like this, and not only is this surjective, so it's exact here, but also this kernel, this principal ideal, we actually know what it looks like. Yes, it's multiples of G sigma, but it's actually isomorphic as a vector space to just a polynomial ring with variables given by the rays of sigma. So here was my picture of a sigma that had two rays, and then we poked it out. And so what we're saying is, if sigma has two rays right here, you just need two variables, and then you take polynomials in those variables, you evaluate them at the tent functions for those rays. You send the variables to those piecewise linear things that we call tent functions for each ray, and polynomials in those variables go to polynomials in those tent functions times G sigma. That's what this principal ideal looks like. And that somehow came down to some previous proposition that we proved before. Once we have this, let's now put it all together and see why the Stanley-Reasoner ring is the piecewise polynomials, why they're isomorphic as rings. So any questions about that proposition that we finished up with last time? Okay, so let's deduce our corollary here. Corollary is actually multiple corollaries. So maybe the first one is not the isomorphism, but some corollaries of what we just did. Well, first of all, corollary one is that actually when you have any kind of a subfan of a fan, when they're both simplicial, so when the bigger one's simplicial, then this restriction map that you get is always going to be surjective. So for any simplicial fan, sigma in RD, and any subfan, sigma prime, that restriction map is surjective. So you got piecewise polynomials on sigma, these map to piecewise polynomials on sigma prime, and it surjects. And the reason is because we proved it in the special case where sigma prime came from poking out one maximal cone from sigma. But whenever I have a subfan of another one, I can poke out maximal cones one at a time to get from the big fan to the small fan. So what am I saying? Repeatedly.
We can do it. Achieve greatness by.
We can do it, and we will achieve greatness. Repeatedly remove maximal cones, sigma, in the big one, but not in the small one, with surjectivity at each step from the previous proposition. Or the previous result. I can't remember if it was a proposition or what. Theorem, maybe. Okay, so just to, be clear on what I mean, suppose I've got sigma maybe looks like this thing that we were talking about before that had, I don't know, these rays here and had some cones in between, maybe, yeah, so here's a three-dimensional cone sigma, and then there's a two-dimensional cone sigma here, and then maybe first you take out this two-dimensional cone. Okay, I guess we could do that in a clever way by doing this. Oh, that's not what I meant. It's not so clever. Remove the stuff that's in there. And then I could start, inside of that, perhaps removing some more, like maybe I'll take out the interior of this one. So I've only got the boundary. And keep going, just kind of work your way through. So maybe I should say that this one was sigma prime, and here we had the sigma prime, and this is sigma minus sigma prime, etc. Just poke them out one at a time. But the point is, these restriction maps we showed in each stage, the restriction from here to here was surjective, the restriction from here to here is surjective, and so a composite of surjective maps is surjective. Now, I'm not going to be talking about sheaves much. Oh, Sam, you have a comment. Wouldn't sigma prime in general have a lot less conditions to less things need to glue together properly? Right, so I guess what you're saying is that the proof where we actually did this construction and showed how if we have these things that are defined on the faces of the cone, that we can always extend a piecewise polynomial over the interior of the cone piecewise polynomially. It's not obvious, right? That there are no obstructions to gluing properly here. And this is actually related to my next comment, which is I'm not going to be saying a lot about sheaves in this class. In fact, after today, I don't think I'm going to say the word sheaf again. But those of you who are taking or have seen some sheaves might suspect that this statement has some rephrasing in terms of some sheaf being flabby, okay, or flask is the French word for it, flask. The idea being that these restriction maps, you can actually think about piecewise polynomials as being the spaces of sections on some sheaf on a topological space that comes from the face poset of the fan sigma. Okay, so there's a way to turn that face poset. A poset isn't a topological space, but you can make it into one. There's a way to make open sets, which are the ideals, the order ideals, and there really is like a flabby sheaf running around here of these continuous polynomial functions, piecewise polynomial functions. And this corollary one is saying that this sheaf is flabby, in a certain sense. It's very well behaved and better than most sheaves. Sam, did I roughly get at what you're trying to say, or are you still bugged by this?
I can still believe it, but I'm still confused as well, because if we go to the extreme case of, let's say we remove everything except the rays, right?
Yeah.
Like
right.
prime is just.
Sorry, you're breaking up, Sam. Yeah.
Then it seems like we can basically. Sorry, I was just saying, if sigma prime is just the one-dimensional cones, it feels like we can just choose those completely independently, and would be like the most possible. I mean, that's like a, I don't know. Maybe again, what you're saying is true. We can always glue them together. So I guess it.
Yeah, you've got, two rays, and you can, extend it over a two-dimensional cone in between, and then over the other two-dimensional cones. And once you've got all the two-dimensional cones that are the boundaries of a triangular cone, you can extend it over there. We showed how to do it. Yeah, it's Flask, it's flabby.
Okay, thanks.
All right, corollary 2. This is the more important one. So let's now do what I was saying we were going to do all along. So given our simplicial fan in RD, I claimed that I was going to take the vertex variables from a Stanley Reasoner ring and send them to tent functions. Let me just do that in a polynomial ring where I know I can make such a ring homomorphism. So consider the ring homomorphism. Oh, a simplicial fan in RD with rays. I'm going to name the rays row 1, row 2 up to row n as usual. And consider this ring homomorphism that just goes completely freely from, commutative ring in n variables to this commutative ring, the piecewise polynomial functions on sigma, and sends the the variable xi to the courant function or tent function rho I. So this is this tent or courant function. The one that it rises linearly as you go up row I, that ray, and it decays linearly down to 0, so on all the other rays that, share a common simplex with row I. All right, and then it's completely 0 on simplices that do not contain the ray row I. I can't even say that, ray row I, ray I. Okay, so if we look at that ring homomorphism, then I claim it is going to induce an isomorphism onto the Stanley Reasoner ring quotient. And it will induce, maybe I should say, I should have ended a sentence, end sentence. Then it will induce, that's our conclusion, a ring isomorphism. From the Stanley Reasoner ring with real coefficients, and I guess it's delta of sigma. All right, so that's this thing, mod I delta 2 here. So let me call this one phi. Maybe I'll call this isomorphism by an abusive notation also phi. It's going to be a map that descends on the quotient. Okay, so this is Stanley Reasoner ring. And we're going to do what you might think. First of all, let me check that this ring map, which was well defined, right? I can always send variables anywhere I want to into a commutative ring out of a polynomial ring, actually does descend to the quotient. In other words, that I delta goes to 0. Let's check that first. Okay, so first things first. Note that if I have a non-face, G is a non-face of delta. In other words, G is a subset of the numbers 1 through n. Then that monomial x to the G, in other words, the product of the things in G, those variables, under phi goes to 0. Because, right, this is what we were just saying about these tent functions. Rises along the ray rho I, decays down to 0 only through simplices that contain the ray rho I. So when you take the product, right, what does this go to? Let's be more specific about where it goes. It goes to the product over J and G of these tent functions for the rays rho J indexed by G. So since this tent function is only supported on simplices that contain rho J, that product can only be supported on simplices that contain rho, all of the rho J's for J and G. If G is a non-face, there are no such simplices. And I guess we should emphasize a non-face of the simplicial complex associated with our fan, right? How did we take a simplicial fan and associate a simplicial complex? We said, oh, make the rays the vertices in our simplicial complex, put a simplex on those vertices, exactly if there was a cone in the fan that contained those rays. Okay, so this is just by definition of delta sigma, and the fact that G rho I is supported on the star of rho I, on the cones that contain rho I. Everybody agree? Okay, so that does show us that that thing descends to a well-defined ring homomorphism, at least on the quotient, because I delta was generated by the x to the g's that were spanned by non-faces, or sorry, the monomials x to the g for g and non-face. So ID, you know, lies in the kernel of phi, and phi descends to a ring homomorphism on the quotient. What am I writing? R of delta sigma. Not at all obvious that it's surjective or injective or anything like that, but we already anticipated this. We put together those two short exact sequences. Now we just compare the two short exact sequences, one for the Stanley-Riesner ring, one for the piecewise polynomials. Okay, so let me remind you, in the Stanley-Riesner ring, oh, and again, pick a maximal face of delta sigma, meaning a maximal cone in sigma. So I'll say a max cone, sigma in capital sigma, with corresponding facet F in the simplicial complex that we associated with this simplicial fan. So for the simplicial complex, it looked like this. We had Stanley-Riesner ring for the big simplicial complex, mapped to Stanley-Riesner ring for the one where we remove sigma, remove F. That's surjected. We identified what the kernel was the principal ideal generated by the square-free monomial for the variables on F. We had some assertion about what that principal ideal looks like, in fact. As a real vector space, we said that it was isomorphic to a polynomial ring with variables indexed by F. And in fact, we knew where to send such a polynomial to get the isomorphism. We just multiply it by x to the f, and that describes what the principal ideal generated by that square-free monomial actually looks like as a real vector space inside of the Stanley-Riesner ring. So this was our very old short exact sequence that we did weeks ago. But then we had this more recent one that we just did. And what was going on there? That was R sigma, the restriction map, R sigma minus that maximal cone. We saw that it was surjective. We saw what the kernel was. The kernel was the principal ideal generated by this product of tent functions, G sigma, for the rays that lie on the cone sigma. We saw that that thing was actually isomorphic to a polynomial ring that are indexed by the rays of sigma. Now remember, capital F corresponds to the cone sigma. So the question is just, are we indexing the rays by their subscripts that are in capital F, or calling them the rays of sigma? And that isomorphism again said, oh, take F, plug in the tent functions. Yes, oh gosh, I'm just going to call them like G rho 1 up through G rho S, and multiply it by G sigma. And so this principal ideal was also isomorphic as a real vector space to just a polynomial ring with variables indexed by the rays of sigma or indexed by the subscripts in F. Okay, that was our most recent proposition, was all of this stuff. And now you realize that, of course, that's the map phi that's sending the xi to the, G rho I. This is the same as this composite restricted here. The xi's are just going to the G rho i's, and it's the same here. So this is the setup for the 5 lemma. In other words, all of the squares in this diagram commute. This map is really just the restriction of the composite isomorphism there on those principal ideals inside. And this one also is the induced map on a quotient, right? This is the quotient of this by this. And so we get induced maps on the quotient. Anyway, right, it's the setup for the 5 lemma. So let me just say now, hence, we can assume this is an isomorphism. Let's maybe say this in red. This is an isomorphism by induction on the number of cones in sigma. This is an isomorphism because it's a composite of 2 isomorphisms. And so one of the instances of the 5 lemma says, oh, if this one's an isomorphism and this one's an isomorphism, and these are short exact sequences of whatever, vector spaces, abelian groups, the middle one also has to be an isomorphism. And all I'm saying there is it's an R vector space isomorphism, but we already knew it was a ring homomorphism. So we're doing induction on the number of cones, which we already did some proofs that used inductions on the number of simplices in delta. So it's a similar idea. Any questions about this? Maybe I should have people look up the 5 lemma or think about it yourself. This is perhaps the most intuitive version of the 5 lemma when you've got a short exact sequence of vector spaces. If the kernels and the co-kernels are isomorphisms, that means you get a vector space on the thing in the middle, the whole space. Everybody okay with this? Okay. So that's helpful. So for simplicial fans, these piecewise polynomials are really a disguised version of the Stanley-Reisner ring. At least we're working over the reals. We're forced to be using real coefficients, notice here. But there's something even better about this. And that is all those linear systems of parameters that I was talking about, these delta of sigmas that sorry, the theta of sigma that I was talking about when I had a delta of sigma, when sigma was a fan. I said, ooh, there's my favorite linear system of parameters. Now you're going to see why it's my favorite and why it works so much better. So that's where I'm going to head next, is talk about the linear system of parameters. Questions before we go there?
So for any simplicial complex, we know we can embed it in some Euclidean space, and then I take it we can put that on a sphere and make it into one of these fans.
Yeah, that's right, Sam, because originally, when I chose to talk about the geometric realization of a simplicial complex, I did it in such a way that it was meant to be part of a fan, exactly in the way that you just constructed it. I picked for each vertex in the simplicial complex, I said, ooh, make a standard basis vector, put it in that really high dimensional space, R to the number of vertices. And exactly as you say, we basically were realizing it like it was on the unit sphere inside of a fan there. But also, this is the way for when we do, the Bergman fans. So when we take the lattice of flats of a matroid, we do essentially realize the appropriate fan in exactly this most inefficient way. That is the fan that we will take. Yep. Good. So yeah, and let's talk about the system of parameters. So this isomorphism interacts really well with the LSOP theta sigma. So I'm just going to remind you, what was that LSOP? It's been a little while since we talked about it when we had a fan. So it was a theta, I'm going to rate it like theta F1 through theta FD, where what were these Fs? We picked a basis for the dual space, an R basis for the dual space of R to the D. So functionals. And what was this theta of F, for a linear functional on R to the D? We said, okay, that thing is going to be some combination of the vertices of delta sigma. And what combination of the vertices? What was the coefficient that we put in front? We said F of V sub J. What the heck were the V sub J's? It looked really unnatural at the time. I picked some vectors that spanned the rays, where the V1 through Vn were a choice. Were chosen to span the rays, row 1 through row n of our simplicial fan. In other words, rho j is the non-negative real multiples of Vj. Okay, that was a mouthful, but I did convince you way back when that no matter how we pick this basis of functionals, we could use them to get coefficients that would make that coefficient matrix, the thing that I constantly am checking the minors to see they have maximal rank, that these things would have the appropriate minors of the appropriate maximal ranks, so that this would be an LSOP. We checked that a long time ago. Now I'm just going to get rid of some of the unnaturality, and you're going to see where these thetas really come from. So what I want to notice is these things, linear functionals on RD, they're actually not just piecewise linear, they're linear. They're globally linear. And maybe now's the time we should talk about, there are piecewise polynomial functions on the fan that are globally polynomial, and they form a subring. So let's talk about that subring. And these things live in degree 1 of that subring. So this raises the point that inside our sigma, the piecewise polynomial functions, we've got the globally polynomial functions. We have the global polynomial functions, f from Rd to R, the set of all of them with pointwise addition and multiplication, as usual, as a subring in our subalgebra. In fact, it's a polynomial ring. In fact, it's a polynomial ring in these folks. You just pick a basis for all your linear functionals on the space. You start multiplying them and adding them, you get the polynomial functions on your space. Everybody good with that? Now, remember, the choice of which F1 through FD you pick as your basis for the dual space, that's just like picking some coordinates on your space. It's somewhat arbitrary, you know, you can make a change of basis, but you got to pick one if you're going to identify with a polynomial algebra. Okay, and yeah, I'm going to name this. Let's just call this thing A for algebra, this global polynomial functions, this subalgebra, the pointwise polynomials. We'll regard, in fact, since it's a subalgebra inside the pointwise polynomial functions, we're going to regard it, the whole set of ring of piecewise polynomial functions, we're going to regard it as a module over the global polynomial functions. We'll regard our sigma as a module over this subalgebra, A. In fact, everybody's graded, graded, and graded, I mean. Remember, we talked about how the piecewise polynomials, they have a grading by homogeneity, cone by cone. Well, that is totally compatible with the usual notion of homogeneous polynomial functions globally. It all interacts correctly. It all works, right? Everybody okay? And now the point is, oh yeah, we used to think about the Stanley-Riesner ring as a polynomial ring over this polynomials in those systems of parameters. We thought about, oh, it's a subalgebra. It's a module over that subalgebra. Yeah, it's the same subalgebra, is my point. That's what we're about to say. Okay, so that's the proposition. Right, given any one of these linear functionals, that ring isomorphism we were talking about, the ring isomorphism, so okay, the direction it went was from Stanley-Riesner ring to piecewise polynomials. It's going to send that thing that I called theta sub f, right? That lived in the degree 1 part of the Stanley-Riesner ring. It was a linear parameter. Phi sends it to f, the linear functional. So remember, this one lives in the Stanley-Riesner ring in the degree 1 part. It was this linear combination of the variables. This one lives in, it's in the degree 1 part of the global polynomial functions. It's a global linear function. You get what I'm saying? And so what does that mean? That means that the if I take theta f1 up through theta fd, they're getting sent to f1 through fd, the things that generate that algebra A, the global basis of global linear functions that generate the global polynomial functions, and hence sends r theta, in other words, the thing we were always talking about, theta f1 through theta fd, that's getting sent to A, the global polynomial functions. Everybody see what's going on here? And somehow, right, if I just hand you that fan in d-dimensional space, this is a pretty natural thing. There's no more choices to make about, ooh, okay, so we got a ring of piecewise polynomial functions. The global polynomial functions, my gosh, that didn't even depend upon the fan. That's even more natural. So whereas on the Stanley-Reisner side, it's a nice object, but it's not quite as natural as that. And boy, those thetas, they didn't sound like the most natural thing in the world when I wrote them down. But over on this side, they seem incredibly natural. Okay, so let's check this proposition and then talk about it a little bit more. It's a little disturbing, frankly. But maybe you should prove it before we get disturbed. Sometimes a proof deferred is disturbing in itself. Okay, it's easy to check. Oh, Galen asks, small question. What is the subscript on the top theta f? No such subscript. Yeah, so my point is, this applies to any linear function that I choose. I had this construction, right? That construction, let me just remind you because we're about to use it. That thing was, you sum over the vertices, the vertex variables, and you apply that linear functional to that, the Vj, which was the thing, remember the row j, we picked somebody, a vector Vj that spans row j. Sound okay?
Sorry, that is a great answer, but I actually meant, sorry, on the bottom line, there's like r theta is equal to r theta of f1 up through theta f1 up through theta f. What does
Sorry
that
about
mean?
that was a D.
Okay, great. Thank you so much. Sorry about that.
Sorry about that. Okay, good. And so let's just check it. Since we've reviewed what theta f is, right? We just said theta f is this thing. And so, not like that, xj. So we know where it's going to go under phi. What did phi do? It sent the xj to the tent function for that row j. And it's linear. And so actually, let me do the following. This is that. And now what I'd like to convince you of is this thing, where theta went to, that piecewise polynomial function. I know it's going to something that's piecewise polynomial. In fact, it's going to something piecewise linear. I'm just going to check what its values are on all of the rays, or rather on all of those vectors vi that span the rays. So let me take a vi and evaluate this, and I get, it's the sum, j goes from 1 to n, of f of vj times g rho j of vi. I'm going to do this evaluation. I'm going to check it for every one of those vectors that spans the different rays. And remember that, right, how do those tent functions work? Row j, the tent function value at vj is 1, and then it goes linearly as we go along the ray. But then it decays down to 0 on all of the other rays. So this is a delta ij. This is a Kronecker delta. It's going to be 1 if the I and the j match. It's going to be 0 otherwise. And so I get that it only matches with VI, and I get that coefficient F of VI. So what did I conclude? This theta F, again in the Stanley reasoning, it got sent to some piecewise linear function that completely agrees with my linear function F on all of those rays, on all of the VIs that span rays. So that's my point. Since phi of theta F is PL, piecewise linear, on sigma, and F is linear globally, and they agree on all of these vectors V that span the rays of my fan, they agree. They are the same thing. So it's a little weird. This thing had a rather strange looking expression as the sum of tent functions, which are nice, and they've got all sorts of weird breaks in them, but we've summed them up with appropriate coordinates to completely smooth out the breaks, and we turn them into a linear function, this global linear function F. We did it on purpose. Remember, okay? Okay, good. And so let me go back to what this was asserting. It says, in our Stanley-Reisner ring, that parameter ring looked weird. In the piecewise polynomials, no, it's the global polynomials. It's the least weird thing in the world. And what might be really, really disturbing about this is these thetas, they looked like they depended upon the choice of the V's, the VIs that span the rays. I mean, there looked like there were a lot of choices in how I wrote down the thetas. And so I want to explain why was that choice illusory, why you really didn't have too much choice at all. Okay, before I explain that, any questions about this proof of what we just checked?
Are you assuming sigma is a full dimensional?
No. No.
So for the like global polynomial functions, they're actually not a polynomial ring. Is that true necessarily?
Sorry, I guess yeah. Let me be careful here. So. Yeah, I can't. You caught me on the same technicality, Sam, as in a previous thing where I said it wrong. I can't call them an LSOP. All I can call them is a bunch of linear elements that give a quotient, which is a finite dimensional vector space. There may be more of them. You're right. If D is larger than the dimension of the largest dimension of a cone in sigma, they're really not a system of parameters. They're more than a system of parameters. So I shouldn't call them an LSOP.
But it all still makes sense, I guess.
It all still makes sense. And it's relevant, right? In the Bergman fan case, the role being played by little d here is going to be R, the rank of the matroid. And the dimension of the space where the fan lives, the Bergman fan, is roughly n, the number of ground set elements. So that case will come up where we have too many of them. They really aren't an LSOP. They're just linear elements and we quotient to make it finite. Yeah. So I do want to find where was the last place where I called them an LSOP. Up here. I should note in red, wrong. Linear elements, let's just call them that.
So basically what can happen is that some combination of them is zero, right? Linear combination of them is zero, is that?
Let's think about this. Right, so what we have to think about, Sam, is when the cone is lower dimensional, that cone, let me just think about this a little bit. No, I think I was about to say something is wrong. As long as that cone has got rays in all directions, then I think no combination of them is going to be completely zero when we restrict it to the cone. Right? The point is, when you're trying to find some that are algebraically independent, yes, how do I want to say it? Let me think about that, Sam.
Yeah, sorry, I'm confusing myself too, I guess.
Yeah.
But I think like that's right, isn't it? I mean, if you had a very small simplicial complex in a much bigger ambient space, you could have linear functions on the ambient space, which would all restrict to the same thing on a smaller dimensional complex, and you would get like some linear combinations in the kernel of that of how they act.
And that is for sure true, Peter. But what I'm worried about is a situation like this. Suppose the rays, all I have is a row 1 that's in the direction of x1, a row 2 that's in the direction of x2, a row 3 in the direction of x3. So it's only a one, my associated simplicial complex delta is just going to have like 3 points, 3 vertices. It's going to be very low dimensional. And so I can't have a system of parameters with more than one element, right? But I just wrote down 3 thetas, theta f1, theta f2, theta f3, and the claim is that, right, I was sending this to A, which is the global polynomial functions. And so what I have to think about is when those global polynomial functions, right? The point is piecewise polynomials on this fan is a ring of curl dimension 1. There are, as a module over this curl dimension 3 ring, there's a lot of quotienting going on, a lot of annihilation. I just have to think about what's the right way to say that. But what is still definitely true is that when I think about that subring, maybe that's the point, is I shouldn't be talking about it as a subring. That's confusing. It's clearly not a subring. Okay. What I should have said is that when we restrict polynomial functions on all of our 3, this thing is certainly global polynomial functions from R3 to R. Right? That isomorphism is fine. But the point is there's a restriction map from those that's not an inclusion. Okay, it has an image, it hits the global polynomial functions on sigma, but there is definitely a kernel, as Sam was saying, right? It's not an inclusion right there. That map has a kernel. Yeah, and if we thought about it in this case, we could think about exactly what that kernel is. Sound right? Maybe. Okay, so perhaps I will say a little more next time about this. I just want to make this remark, and then we will be done. So the point is, the theta FIs looked very non-canonical. Like they depend on the choice of the VIs. Spanning the rays. Right. But here's the thing. When you got one of these rays here, and if you change that VI, suppose you scale it up and down, just dilate it or shrink it, whatever that scaling factor is, but replacing the VI by some CI VI, with say CI, a non-zero real number, you can achieve the same effect back in the Stanley-Riesner ring. The variable that corresponds to row I, there's going to be an xi, one of the vertices in your simplicial complex. You take its vertex variable, you do the inverse scaling to it, xi divided by ci as the effect in the Stanley-Riesner ring of scaling the variable xj by, xj divided by cj. These are ring automorphisms. You know, the Stanley-Riester ring, it was polynomials in x1 through xn, you mod it out by some monomials. You're allowed to take those vertex variables, scale them by non-zero scalars from your field. Those are ring automorphisms. You can check, and they will change your thetas in the appropriate way, so that if you rethink who the generator is for the ray, you're just going to be changing the slope of your tent functions, basically. But you can change the Stanley-Riester ring in an analogous way. You can perform an automorphism back in the Stanley-Riester ring so that it has the corresponding change. That's why these things looked weird, is because, you know, it has to do with this possibility to rescale variables in the Stanley-Riester ring and still have something isomorphic to the Stanley-Riester ring. That's okay. All right, maybe that was still disturbing, but I will think a little more about Sam's question next time by pondering this example. Questions before we turn the video off?
So this last comment, we kind of get like a torus action.
Exactly.
Is it related to the theory of torque varieties, or?
I think so. Actually, Sam, it's related to a research question that I asked you a few days ago. It's that torus action. Yeah, it is. And I think the point is, when we're thinking about the parameter space for the thetas, really there's like a Grassmannian going on, and this is the torus action in that Grassmannian. Yep. Okay, other questions before I turn off recording? All right.